Welcome to my video course on communications-based train control. You know, if you've ever stopped to wonder how on earth modern cities safely run massive, heavily loaded metro trains literally just 90 seconds apart, well, the secret is all in the incredible evolution of train control. So today we're going to break down the exact mechanisms that transform those rigid, old-school railways into truly dynamic transit arteries. Let's get right into it. Okay, so here's our roadmap for today. First, we'll cover the need for signaling. Then, we'll look at the fixed block bottleneck. After that, we'll trace the evolution of train control, dive into the moving block solution, and finally, wrap up with how this all enhances railway capacity.
All right, Section 1, the need for signaling, physics versus railways. So why do trains actually need signals in the first place? Well, it essentially comes down to a fundamental physics problem. Unlike driving your car, right, where you can just slam on the brakes if a deer jumps out, trains are thousands of tons of metal gliding on ultra-smooth steel rails. It creates incredibly low friction. Honestly, it's a lot like trying to stop a massive oil tanker on ice. Because of this, you absolutely cannot drive a high-speed train by sight alone. By the time a driver physically sees an obstacle ahead on the tracks, it is mathematically impossible to brake in time.
To put that into perspective, let's think about the safety distance requirements. If a train is moving at, say, 100 kilometers per hour, it requires a massive stretch of track to safely stop under worst-case failure conditions. To prevent a totally catastrophic rear-end collision with the train ahead of it, traditional systems are forced to enforce a strict, non-negotiable 1-kilometer block of completely empty track between them, just a massive buffer zone. Which brings us to Section 2, the fixed block bottleneck, wasted space. Because the track is hardwired into these rigid, fixed blocks, we end up with this really severe artificial separation. Imagine a second train occupies a specific block up ahead. The train behind it is automatically stopped at a red signal one entire block back. And here's the crazy part. Even if that trailing train is just creeping along at 20 kilometers per hour, it is still forced to stay behind that massive 1-kilometer safety buffer. That buffer was originally designed for top speeds, not crawling. So what happens? It creates vast amounts of wasted, unutilized track space between the trains. Now, to reclaim all that wasted space, engineers came up with a really brilliant concept called movement authority. Instead of relying on a physical green or red light bolted to the side of the track dictating if a massive block is clear, permission to move is established dynamically. A central computer, which we call the zone controller, calculates exactly how far a train can safely advance, right down to the meter. And it does this based on the highly accurate real-time positions of all the other trains on the network. It's a real game changer.
Okay, moving on to Section 3, evolution of train control. We actually evolved through a few very distinct eras to get to where we are today. Era 1 was the absolute block system, which was heavily reliant on human station masters manually clearing a train from one station to the next. Era 2 brought us automatic block signaling, which used electrical track circuits to detect if a train was there. Then Era 3 was cab signaling, which finally brought signal displays directly inside the driver's cabin, allowing for smaller blocks. And finally, we arrive at the present era, communications-based train control, or CBTC for short.
And there is a drastic difference in how speed limits are handled here. Traditional signaling relies on a static speed profile, meaning speed limits drop abruptly in these rigid block-based steps. But CBTC, it enables a dynamic speed profile. The train's onboard computers are continuously calculating a super smooth, real-time braking curve. So instead of just reacting to a fixed arbitrary chunk of track, it is beautifully adjusting its speed to match the exact, precise location of the danger point ahead.
Let's dive into Section 4, the moving block solution.
This is really where the magic happens. The safety envelope actually becomes a fluid, moving block. Through continuous two-way radio communication, the train is constantly transmitting its exact position, its speed, and its braking capability. Wayside computers then take that data and instantly calculate a tailored safety buffer that literally moves right along with the train. So multiple trains can safely pack closely together, separated only by their true braking distances, rather than those artificial geographic blocks we talked about earlier.
And finally, Section 5, enhancing railway capacity.
The benefits of this for modern cities are absolutely massive. First off, it eliminates the need for costly physical track blocks entirely. And miraculously, it reduces headway, the time between trains, to as low as 90 seconds. Think about that. You can have a fully loaded metro pulling into the station just a minute and a half after the last one left.
Plus, it dynamically regulates the trains based on passenger demand, and it even enables completely driverless operations. The system flawlessly handles safe movement, precision station stopping, and even automatic door operation without a single human needing to be in the cab.
Ultimately, CBTC truly transforms rigid railways into dynamic, high-capacity transit arteries. By replacing fixed track limitations with real-time wireless communication and these incredible moving blocks, we are able to squeeze maximum efficiency right out of our infrastructure. This technology ensures that modern cities keep moving safely and efficiently. Thanks, we can see you in next video.